Gloria Rubin once said that the transition to clean energy is the equivalent of investing in our future. The seventh goal of the 2030 Agenda for Sustainable Development is to ensure access to affordable, reliable, sustainable, and modern energy for all. As a member of the United Nations, South Africa has taken ownership of its responsibility in achieving this goal by incorporating alternative energy sources, such as wind energy, into its energy supply chains. Wind energy is one of the most prevalent industries in power supply globally and is currently seen as the fastest growing and most effective alternative energy source worldwide. The use of wind energy as an alternative energy source in South Africa has become more prevalent in recent years, with more than 10 wind energy projects currently underway. This project aimed to design a wind farm and substation to supply a modern residential area in Gauteng consisting of 1,000 households. In this presentation, we will take a closer look at the following aspects of the wind energy project: the wind farm, the substation, and the maintenance strategy. Let us start by looking at the wind farm.
First, we will consider some key components of the wind farm. The first three components that we will consider are the spacing, layout and situation, turbine and drivetrain, and the propeller design. With regards to the spacing, layout and situation of the wind farm, the situation of the wind farm should be on top of a flat hill with little to no vegetation. This is due to less friction being experienced by the wind. In terms of the turbine and drivetrain, they play a crucial part of the design. They house the generator and the gearbox. For our design, we will be using a single-stage gearbox over a three-stage gearbox. This is due to a single-stage gearbox having less maintenance issues. The propeller design that we will be using are curved blades instead of flat blades. Curved blades are similar to that of aeroplane wings, and they have low pressures created at the top, and this allows for more lift forces experienced by the blade. Next, we will consider the following three components of the wind farm: the angle of attack, rotor diameter and length of blade, the wind turbine tower, and the transmission lines. The angle of attack that we will be using is 15 degrees with a rotor diameter of 75 meters and a blade length of 50 meters. These values were researched and calculations were done to ensure an efficient design. The wind turbine tower shape that we will be using will be cylindrical, as this will cause less friction for the wind. In terms of the transmission lines, we will be transmitting the power at 11,000 volts and 450 ohms. This is done to ensure the least possible wastage of power.
The foundation of the turbine is made of concrete reinforced with steel rods to support the tower. The tower is made in a tubular shape of steel and composition with aluminium, cast iron and plastic. This shape allows for wiring inside. The blades are made of carbon fiber and glass fiber. This makes them stronger and lightweight.
As for most modern complex systems, a control system is required to manage the main functionality of the system. The system is based off of modularity for better performance of the wind farm. The system is split into two parts, a central control system and an individual control system. The central control system has an AI built in with a complex pattern detection algorithm. With this, the AI can predict power output, performance and lifespan of components in the wind farm. The individual control system manages all the sensors in the turbine, and with the data from the sensors, the control system calculates when to pan the blades of the turbine for maximum power output.
Next, we will look into the substation design. The design of the substation can be divided into three main parameters. All three parameters have design considerations based on optimizing the maintenance strategies of the substation and minimizing the energy losses. The first parameter looked at in the substation design are the transformers. The substation will step down the voltage received from the wind farm using 11 to 3.3 kilovolt step-down power transformers. 2 step-down transformers will be needed per circuit feeding into the switching yard. This is because a dual feed technique is used to feed the switching system. The voltage is stepped down to 3.3 kilovolts as working with this voltage range minimizes energy losses. The next parameter focused on in the design of the substation is the switching yard. The switching yard aims to isolate any faults in the circuit so that complete power is not lost in the entire substation. Furthermore, this aims to assist with maintenance strategies as only the damaged circuit portion will need to be replaced rather than the entire circuit. The switching system chosen for the substation design is a ring bus switching system. The transmission lines to the residential area make up the final design parameter of the substation. Overhead lines will be used to transmit power to the residential area and will be held up using wooden poles. Wooden poles are chosen as they are cost effective and the transmission lines only need to cover 3 kilometers. The transmission lines will be transmitting 3.3 kilovolts to the residential area as this is sufficient to minimize energy losses.
Next, we will look at the materials that will be used in a substation. Steel pylons carry high voltage transmission lines made of aluminium. These lines are received by a dead-end structure in the substation. Other components in the substation are supported by bus supports. Dead-end structures and bus supports are made of galvanized steel for high strength and to prevent corrosion. Sound rocks are laid on the surface because they have high resistivity and keep wildlife away.
Next, we will consider the substation control system. The substation control system is implemented as a SCADA system, which is a hardware and software network that automatically monitors substation processes, enabling efficiency and well-informed decision-making. The central server of the system is hosted on a computer that communicates with RTUs and PLCs, which translate in-system and sensor output data into digital data that is sent to the server to be processed. Operators interface with the system via an HMI. The control system manages switching processes, transformer operations, distribution feeders, and electricity storage in battery banks. Various sensors, digital meters, switches, digital relays, circuit breakers, alarms, fuses, and IDs are connected to the system. Condition monitoring sensors collect equipment data for early malfunction detection and to warn the operator about necessary maintenance. The system restricts access to unsafe equipment, ensures that only approved personnel access the substation, and monitors the Gauss meter. The system uses AI for pattern detection and to decrease the need for human supervision.
The chosen maintenance strategy for the wind farm and substation is a total productive maintenance strategy, also known as TPM. The TPM strategy is built on 8 pillars, namely autonomous maintenance, focused maintenance, planned maintenance, quality maintenance, education and training, safety, health and environment, office TPM, and development management. These 8 pillars ensure a holistic maintenance strategy. The 4 pillars seen on the left-hand side can be seen as the core focus areas of the maintenance strategy, whereas the right-hand side indicates the vehicles that drive the strategy. Autonomous maintenance aims at building quality into the process by training operators in basic routine maintenance procedures and early fault detection. Autonomous maintenance also includes the incorporation of ICT and AI, such as condition monitoring systems and SCADA systems, to automate maintenance feedback systems. Focused maintenance aims to eliminate losses that occur in wind energy production, such as losses due to failure, setup losses, speed losses, defect losses, startup losses, idling losses, yield, and minor stoppages. Planned maintenance refers to the scheduling of all routine maintenance tasks that rely on accurate failure predictions and are greatly influenced by environmental factors such as temperature, wind speed, humidity, vibration, rainfall, and lightning. Quality maintenance is closely related to autonomous maintenance processes, as it aims to eliminate avoidable maintenance tasks and optimize unavoidable maintenance tasks.
Safety measures in the wind farm and its environment. It is important that the correct safety measures are implemented to ensure the safety of personnel, civilians, and all parts within the wind farm and substation. Safety equipment in the wind farm and substation, such as safety lights for low-flying aircrafts, safety netting and harnesses for maintenance staff working on turbines, first aid equipment for safety, and an alarm system alerting all personnel of possible hazards within the facilities. There are fingerprint access systems implemented in both the wind farm and substation, allowing only trained personnel access into both facilities. The wind farm and substation should not be located near residential areas, as the large wind turbines pose a threat to civilians in the event of disaster, and substations emit electromagnetic fields which could be harmful to human beings. Risk assessments need to be set up to evaluate all parts of the wind turbines and substation that pose a threat to personnel, civilians, or parts of the turbines themselves.
The correct choice of wind farm components ensured an efficient design. The use of step-down transformers in the substation enabled voltage to be transferred at very high rates. The TPM strategy as the optimal maintenance strategy allowed for both preventative and reactive maintenance perspectives.
The wind farm and substation were designed for maximum power generation using optimal layouts and carefully selected component materials, hence the project is feasible. The control system, safety measures, and maintenance strategies were carefully considered to support the operations and ensure efficiency. Improvements on the study can be made through further research on drivetrain gearbox efficiency, blade size analysis, transformer power rating, SCADA AI, and mathematical modeling and maintenance.